My name is Sergey Slizovsky. I'm a research associate in the theory group at National Graphene Institute, the University of Manchester. I'm going to talk about the cascade of Lifshitz transitions in surface states of graphite aligned with hexagonal boron nitride. First of all, I would like to acknowledge my collaborators. Experiments were done by the group of Artyom Mishchenko, and a theory part was done in collaboration with Vladimir Falko. Graphite, I present the difference of Bernal and rhombohedral stacking order. For convenience, I will focus on thin flakes of graphite, but all the content of my talk applies equally to the surface of infinitely thick bulk graphite. In rhombohedral graphite, every atom is dimerized with a neighbor just above or below it. For thin films, this leads to shifting of bulk bands to higher energies. The only exception are non-dimerized carbons in the top and bottom layers, shown in red color, which host low-energy surface states. These surface states have very shallow dispersion and hence are promising candidates for hosting strongly correlated states of electrons. But these are not the topic of my current talk. In the more abundant Bernal stacking, half of carbons are located above each other, forming vertical chains with large hoppings. The other half appears to be in between the empty centers of honeycombs. Hence, it is weakly hybridized and hosts a lot of low-energy states in graphitic film. So, Bernal graphite is a bulk semimetal, which a priori does not have any surface states. Nevertheless, surface states do appear upon electrostatic doping, and this will be the topic of my talk. Here I show the dispersion of bulk Bernal graphite. It can be parameterized with a set of 6 Slonczewski-Weiss-McClure tight binding parameters. There are 3 types of carriers: electrons, holes, and minority carriers near the H point. The two-dimensional bands for thin films of Bernal graphite can be understood by quantizing the momentum in z direction and slicing the bulk dispersion. The bands look like touching electron and hole parabolas for generic Kz and as slightly gapped Dirac cone at the H point. The self-consistent Hartree calculations show that evanescent modes near the surface appear if the surface of graphite is electrostatically doped. An example dispersion is shown in blue-red figure, where red color indicates the surface bands. To qualitatively understand the possible surface states, let us for a moment fix the in-plane momentum and plot the dispersion as a function of complex momentum in z direction. Then, for small in-plane momentum, we have a one-dimensional metal, and the evanescent modes with complex Kz can appear only away from the Fermi level. At large in-plane momentum, we have a one-dimensional semiconductor, where evanescent modes can appear at the Fermi level. So the Fermi contour of the surface states appears for in-plane momentum larger than the size of the bulk Fermi surface, and it grows with the doping. The blue-red figures show the bands for 14-layer graphite for different levels of electrostatic doping. Blue color are bulk bands, and red color indicates the surface bands. The diameter of the surface band Fermi contour grows with applied doping, increasing the total density of surface states, as has been verified experimentally with quantum capacitance measurements. An effective penetration depth of external potential into graphite is approximately 2 layers. The surface states can be viewed as the states trapped in the one-dimensional electrostatic potential well near the surface. As usual, with growing depth of the well, more bound states can be trapped near the surface, forming several surface states bands. Now, there is a nice way to probe and modify the surface states. Let us align graphite with boron nitride. Graphene and boron nitride have similar hexagonal lattice, but boron nitride have 1.8% larger lattice constant. Aligning graphite with boron nitride leads to famous Moir pattern with period around 40 nanometers. A periodic potential of Moir pattern leads to non-zero matrix elements between states with momenta that differ by Bragg vector of Moir pattern. Elementary perturbation theory tells us that the Fermi surfaces are strongly affected only when they can be connected with Moir-Bragg vector. The bulk graphite Fermi surfaces are smaller than the length of Bragg vector and so are not affected. But the Fermi contours of the surface states grow with the surface doping achieved by applying the gate voltage. At some critical doping, the Moir-Bragg vector starts to connect different points on the Fermi contours. With higher doping, two branches of the surface states get mixed by Moir-Bragg scattering. When we calculate the new band structure, taking into account the Moir perturbation and plot it in the mini-Brillouin zone spanned by Moir reciprocal vectors, we see a cascade of Lifshitz transitions. Electrons start turning in opposite directions at the corners, so that the Fermi contour reconstructs from electron to hole type. With growing electron doping, the second and the first branches of the surface states start to be mixed by a Moir scattering process, turning the second branch of the surface states from electron to hole type. A similar picture is seen for the hole doping. Here you see experimental data for hole conductivity and magnetic resistance at small magnetic field, plotted as a function of electrostatic doping. At the Lifshitz transition points, the hole conductivity sharply jumps due to changing direction of electron drift around the Fermi contour. At the same time, the resistance drops near the Lifshitz transition because the Fermi contour becomes effectively open at the transition points, and electrons are no longer confined to drift around a single closed contour. When we are close to Lifshitz points, electrons can still tunnel through the saddle point, increasing the conductivity. This is called the magnetic breakdown. To summarize, Bernal graphite hosts surface states when doped by application of gate voltage. Surface states coexist with bulk semimetallic states but occupy larger in-plane momenta. Fermi contours of surface states grow with doping, and with growing doping, new surface branches appear. The size of the surface state Fermi contour is comparable with Moir-Bragg vectors that appear if graphite surface is aligned with hexagonal boron nitride. This induces Lifshitz transitions, leading to changes in the Fermi contour topology. Topological changes in the Fermi contours are reflected as jump-like change of sign in Hall coefficient and a dip in resistivity.